Batterie 0%. Connecté à MICOLAS HP.
All right, we can start. It's good. There's a snowstorm, but it looks like most people are here anyways. That's the fun part about Zoom. So where were we last time? Oh yeah, here we were. Okay, so today we finish very quickly the introduction, and then we hop into chapter 1. So compared to last time, I'm maybe like 10-15 minutes behind, but otherwise it's perfectly good in time. Okay. Okay, so nature of economic analysis. So just to tell you where we were, so what we were discussing. Yeah, so environment and stuff like that, right? So that's what we were discussing. Okay, so very briefly, so this is something as most of you know, I guess, that economics has 2 dimensions to it, so positive and normative. Positive is not being cheerful. It's about describing what actually happens. So what is, how things work. So we develop models to try and understand how things are as we observe them, and hopefully make predictions about how things will happen in the future. So it's obviously models about how we think people react to stuff. So things like people react to incentives. What does that mean? It means if I make you pay more to do something, for instance, then probably you're going to do less of it. That's a theory about how things work. We expect that if we implement a tax or give a subsidy, then it's going to change people's behavior, and that's what we want. So this is the positive aspect of it. So for instance, in what concerns us, so property rights may contribute to an efficient redistribution of pollution. So reduction, sorry, of pollution. So you're going to see what we mean by this when we discuss Coase theorem and property rights. Yeah, so the scientific aspect of economics is based on it. So is economics a science or not? Who knows? We do our best. It's just we have hard data to deal with. People are unpredictable and complex, and societies are complex. But still, that's what we hope we're doing as much as possible. And then the normative aspect of it. So should we do something about the climate, about pollution, about resources? Well, so this is a question about should or shouldn't. So it's what we call normative. So obviously we use our positive analysis of the world to say, well, if we want to do something, then this is how we should do it. So example, we should distribute property rights. So Oh yeah, okay. So how do we do it too? So do we? So this is, yeah. I should have expressed this better. So do we give property rights to people who receive pollution so that polluters pay for their pollution, or do we say that people who pollute have the right to pollute, and then it's up to people who don't want pollution to pay them? So this is it's a question of redistribution. How do we distribute property right? What will work best? Then there's all this aspect of norms, basically. So all of these examples are, so for now, it might be a bit hard to understand, but we're going to see most of them later. And disagreements exist among economists on what we should do mostly. So on the positive aspects, economists mostly tend to agree on the basics. But then if you ask them, so then tell us, should I do this or should I not do that? And generally economists will say, yeah, on the one hand, this will happen. On the other hand, that might happen. So I don't know. I don't want to decide. You decide for yourself. So we're always uncomfortable saying something for sure. And that's, yeah, it opens the floor to debate among economists. Different economic criteria. So we say that an outcome is economically efficient if the resources have their highest value use. So we're not saying what you should do. What you should do is a normative statement, and as we've seen, it's more complicated. But once you say this is what I want, as this is the production I want, or this is the amount of pollution I want, then what we care about is to achieve this at the lowest possible value. So, for instance, if you say we should reduce CO2 levels, well, economists will say, well, how can you do that if you have if you can do it this way or that way or that way or that way? So you should do it such as yeah. So it's the least costly for you to do it, at least. Otherwise, people are just not going to want to do it if it's too expensive. Equity is one. So this is just about efficiency. It's about maximizing output or minimizing costs. Equity is about how things are redistributed between different groups. As I said previously, so in environment, there's a question of polluters and mostly rich countries or advanced countries versus very poor countries, or future versus present generations. So this is a criterion that we can introduce, but as soon at least this one should. So this one is priority. Right, so this we are good at it. This one is more complicated, but yeah. Poor versus rich, present versus future. Yeah, distributive impacts of environmental policies. So if you do something, then it probably has redistributive impacts. Yeah, so yeah, one example I could give is in Quebec. So last class I gave cost-benefit analysis as work to do by students, and one worked on the subsidies to electric cars. And he said, well, a subsidy to electric cars is a subsidy to cars that are quite expensive. So subsidizing a product that is consumed by people high income already. So it's, you could see it's regressive. So Quebec does not subsidize luxury electric car, but still just an electric car isn't a cheap car. And it says something about the fact that the person still wants to buy a car. So you have to think about this thing too. So if we tax poor people to give electric cars to rich people, I don't know. That's a debate we may want to have. Yes, Mr. Lucier.
I have a question. Maybe you'll have the answer. I read the newspaper pretty much every single day. I follow the stock market every single day. You have probably heard that today there was a big subsidy, well, money given to Bombardier once again, which was about $200 million. We've already given 1.2 or 1.3 billion dollars. If we look at a subsidy like that, I guess we would take in consideration more the present versus the future rather than the poor and the rich, I presume.
So what was the goal? Why would they do that? I haven't read it.
The whole reason is to fund the C series. I'm a big airplane fanatic. That's why I kind of know all of that domain. But the C series, which is the airplane that they are building at the moment.
But didn't they sell
Airbus.
that already?
It's with Airbus. So they're I guess it's a way of keeping the jobs in
yeah.
in Mirabel. I think that's what it is more than anything else.
Yeah, I'm not too sure about all these subsidies. So a bunch of many times it's deals that we don't know too much about, and economists are not too. I wouldn't comment without knowing more, but yeah, this kind of subsidy too. I mean, it would make a bit more sense to me if, for instance, electric cars were produced in Canada or Quebec, and you say, okay, at least we're sort of creating good jobs, but now it comes from California or other places. So yeah, so in that case, yeah, probably jobs, probably yeah. All right. But so it's not good for the environment, that's for sure. Yeah, methods of environmental and economics. So mostly microeconomics. That's what we are going to do mostly this semester. So it has to do with studying the decisions of agents, consumers, and producers in specific markets. So you can think of the market of organic apples, or the market of electric cars, or specific markets, and then we can abstract from the other markets, because the general equilibrium models in macroeconomics are more complicated, and here it does the job basically. So this is the bread and butter of environmental economics. So we could still study with macroeconomics. It's useful to when we look at huge problems, long term, when interest rates are important, inflation is important. So I guess a problem like the whole climate crisis, if you have to have a very long-term horizon of 100 years, maybe, so then you can start thinking about the economy as a whole, because it's really it affects all the markets at once. So you can have larger models. Don't worry, we're not going to have this in this class, but yeah, know that we can still do that. Econometrics, so everything that has to do with collecting data and analyzing it, so knowing how people react to stuff, if supply or demand is inelastic, what's the impact of what's the impact of carbon. So this is mostly maybe a physical But anything that has to do with estimating models that we come up with in microeconomics or in macroeconomics, at some point you need data. So, and then to analyze it well and to come up with good answers and good so good estimates of these models, then you need econometrics. So I'm not going to ask you to to use econometrics since you're quite not too advanced in this field, but know that it's coming for you if you continue in economics. All right. Types of equilibrium we're going to see. So this is linked to microeconomics. So microeconomics is partial equilibrium mostly. So it's a single market at a time and a small number of markets. And it abstracts the rest. So it assumes that the impact of the other markets or on other markets are negligible, no feedback loops. So it's not the case that if the price goes up, it's going to backfire and change something else in this market. So we assume that we can just look at one side of things and not care too much about the rest. Markets are small, of course, but because if we look at very large market or many markets, then it's the whole economy, and you have to use a general equilibrium for that. So a good example is a position in a small river. So you just see it's so whatever changes in terms of how much people produce in the around the river, it's not going to have a big impact on, say, prices or net create inflation or all these things. So you can just study this problem on its own and not care about the rest. Again, this is mostly what we do in this class. General equilibrium is the totality of the economy, more complex, better adapted for important markets and large market. So integrated evaluations of climate change. So that's, more difficult. Less reliable. So why do I, not less reliable. I don't want to judge. What I want to say is more difficult to estimate. Accurately. Purely because it's you need so much data, and maybe you have some good fit for the model in this decade, but not the next decade. So you're going to see all of this when you continue in macroeconomics. Personally, it's not my cup of tea. I rather do econometrics with mostly micro problems or labor market, for instance. I alluded to this before. So the related disciplines to environmental economics. So it's linked to public economics. So everything that has to do with government intervention, because of externalities, because of public goods. So this is it's relevant for environmental economics, but it's also relevant for health. It's relevant for whatever. If my neighbor has loud music, then it's an externality. So it's the same analysis. So this is all under the umbrella of public economics. But yeah, public economics is also interested in taxation a lot. Voting rules, so many other things. So we don't go there, but these two parts, especially. And the economics of natural resources. So environmental economics is quite recent. It's really appeared mostly after the 1960s, but natural resources, it's since maybe more than a century. people have been worried about going out of resources. So it models the optimal exploitation of and extraction of renewable resources and non-renewable resources. So for our sakes, maybe renewable resources are more interesting in the sense that what's the optimal pace of exploiting a gold mine? Who cares? It's really so it all under the umbrella of optimal control, and it's all differential equations, and it's very technical. It's if you want to make a lot of money with your mind, then you study this, but that's not we don't care too much about it. But still, we care about natural resources. Okay, so this is a good point. Math level required in this class. So no derivatives. Did I write this down? Yeah. No derivatives. Which makes it challenging for me, but no derivative, I promise. Simple. So what you have to be able to do is represent graphically functions that are going to be linear, interpret the graphical representation, solve a system of two equations, two variables. This is something that many of us learned in high school, but it's okay to have forgotten if you haven't done too much. Still, you should have seen a bit of this in microeconomics in 201, although not as much as in this class. Finding the area of triangles and trapezoids. Do not hesitate to ask questions. So this is the really, I know it can be scary, or maybe you think it's embarrassing to ask a question, but just people, it takes courage to ask a question. So if you do, then people are going to say, yeah, so okay, that person didn't know, but at least it's thank God that person asked the question. I had the same question, and it's so please do not hesitate. That's the name of the game. Okay, so we're done with the introduction. If you have something to say, or go ahead. If not, I am going to jump to the next chapter. All right. So what's the next chapter, by the way? Oh yeah, okay. Oh, that's a fun chapter. All right. Okay. So we're going to discuss a bit more what we mean by pollution, types of pollution, pollutants, how to address them, but not how to address them from an economic perspective yet, just from a technical or physics or concrete way. How do you address it? And then the economic part of it is how do you make people use different tools to address it? And why do we care about this? Well, we care about this because it's useful to describe well the problem so we can study it well. So this is something that I want to convince you to convince you is important, is to be precise. it's a big problem with the environmental debate in the world is that people don't have numbers in their head or they have impressions. But so at the end of the day, if you want to be effective, if you want to come up with good policies, there's no going around it. You have to ask yourself what the numbers are, what the consequences are, how much it costs, and then we can have, so at least we have a common ground, and then we can come up with efficient solutions. If you don't have that, then you're in a bad spot. Okay, so what do we mean by, first of all, natural capital? So natural capital, I think I said it briefly in the introduction. So it's the stock of natural and environmental resources that sustain our ecosystem and economies. So economies depend on the natural capital, such an ecosystem, and economies depend on the ecosystem as well. So everything is linked together. So what is natural resource capital? So it's the stock of renewable and non-renewable resources. So non-renewable would be minerals, energy stock, but those two are different, right? So minerals, if you dig it out of the soil and you use it, but then you throw away imagine it's in your phone. If you throw the phone away, okay, the mineral is kind of lost, but not really, because it's still in there. Energy stock is different in the sense that if you burn it, then you don't get it back. So even though there are two non-renewable resources, they're sort of different in the sense that this one you can recycle and that one you cannot recycle. Then renewable forests, water, fisheries. You can also say that forests, I don't know how much, so the forest industry is going to say, oh yeah, but we replant again when after cutting. Yes, but if that, so you have to think back in the days when explorers explored Canada and Quebec, they had huge trees. Nowadays, these trees take decades or hundreds of years to grow super large, and it takes a long time for nature to really for the whole natural process to appear in forests. So my whole point is that, so forests, okay, you can have a tree plantation. Is that equal to a natural forest? That's a good question. So Yosemite is a natural forest, but yeah, tree plantation, not too sure. Ecosystem or environmental capital. So that's atmosphere, waste assimilation provided by forest. So this is, so these are the resources that you use, and this is what you would use to process, not pollution, but process rejection by nature or by the economy. Grassland, wetland, and then land. So these are the three, it's a way to classify capital in three categories. So what we mean by natural denotes the ecosystem and their component parts. Capital represent that nature has different functions for it being capital. So it's a store of value, because we can use it to generate production. That's so it's capable of producing goods and services. So yeah, but it's also a store of value in the sense that if you don't use it, it's still there and you can use it at some point. So it's stored there, but it's depletable, because once you use it, then it's not sure that you can get it back. All right, impact of natural capital use. So using capital reduces the stock available in the near future. So catching too many fish today mean fewer fish to catch in the future. Yeah, of course I will be posting them on Moodle. Yeah, for sure. That's the whole purpose of it. No, you don't waste time copying everything. I want to go relatively quickly. Catching too many fish can deplete catches in the future. Do I? Oh yeah, I don't have. I'll try to remember. So, do you know a bit? Somebody knows what is how we can model stock of renewable resource and exploitation? Yes, no, maybe. So it's a logistic curve. Yeah, PPF. So this is so prediction possibility frontier is something that's a bit static in the sense that we don't really care about, we don't think too much about dynamics. But so how this works is, this is more advanced, but still I want to so I'll try to remember how this works. So growth. Whoa. Okay. Equals this tau is some it's just some number that's a sort of natural growth rate times stock times carrying capacity minus the stock and minus harvest. All right. So this is more advanced, but if you just go study more natural resource economics and renewable resource, that's what's going on there. So this is what we call a logistic growth. And why? How do we understand this? Well, how fast is the stock going to grow? So if I have fishes, how much new fish are going to appear? Well, if I start with a very large ocean and very few fishes, then they have lots of place to go into. So the proportion of the growth rate will be proportional to the stock of the fish. So if I have 4 fish, then the population is going to grow twice as fast as if I only add 2 fishes. So because it's exponential, it's more fish, more offspring. But then there's this second thing that's kicking in, which is called the carrying capacity. This is how much fish I would have in total if I let them grow forever. I wouldn't have an infinite amount of fish. I would have at some point the fishes would grow in all the ecosystem, and that would be it. And this is minus the stock. So you see that the growth is going to be 0 if the stock is 0. If I have no fish, it doesn't grow. Or if the stock equals the carrying capacity, then I have this minus the stock, which will be 0. And then this is just a constant. So this is so it looks like if you start, it's going to grow fast, and eventually it's going to stabilize. So that's logistic growth. And then there's a harvest here, and harvest is how we affect future growth. So if we don't harvest at all, then we don't have any fish. But if you harvest all the fishes, then the stock goes to 0, and there's no growth anymore, and we can't harvest anymore. So harvest today impacts future growth. future harvest possibility, future stock, and future harvest. So I'm not going to ask you to remember this formula. This is something for natural resources, but yeah, just to, if you want to have a more technical representation of it. Residual are created by the use of natural resources. So if you use it and create pollution, and waste may deteriorate natural capital too. So if we put too much pollution in the environment, then fishes may not reproduce. Nowadays, all fishes have plastic in their guts. Is that good? I don't think it's good. It's too soon to know how bad it is. Maybe it's not that bad, but I wouldn't be too thrilled about it. And by the way, we all have plastic in ourselves right now, of course, because we eat fish. I don't know. I don't know how it feels if having plastic in yourself is good or bad. All right. Yeah, so what we study in natural resource economics is how to efficiently use natural resources over time. And the type of resource dictates the optimal exploitation. So if it's renewable, so you want to why isn't, so this is, okay, this is good. So some yeah, optimal stock, I would say. Optimal harvest. So if it's non-renewable, then you care about the optimal speed of extraction. Yeah, so example of living resources, fisheries, timber. So this is what I just said. So extraction rate affects future availability. So if I let a forest grow longer, then I get more trees to harvest. So what's the optimal time to harvest them? So that's the question if you have optimal resources. Oh, so here's my formula. Okay, all right. Oh, I'd forgotten I put it there. Sorry about that. Yeah, so I already explained it. And non-renewable, yeah, then you have solar energy. So solar energy, that's the neat thing about it. You don't lose it. Wind power, you don't lose it. Hydropower, you don't really lose it. So, that's what's neat about non-living renewable is basically you can go on forever with it. Non-renewable or very slow regeneration, like oil, fossil fuel. Then if you burn it, you lose it. Non-mineral, non-energy mineral deposits, you can still recycle it, but recycling may be difficult. So. Okay, so how fast should we extract oil? So people can ask themselves this. So if we look at how much oil reserves do we have today, we have this amount of barrels approximately in the world. So that's 1 million billion, so that's trillion barrels. so 1.6 trillion barrels estimated, but even if we have new discoveries, we don't discover all that much new reserves. So we're sort of what we have. And how much we consume each year. So 35 billion barrels per year. So it means that every year we can just divide this by this, and we find that we consume about 2.5% of our reserves. So it means that at this rate, we would be done in 47 years, which is looks like it's very soon. So if you just input this, what's wrong with this number? Well, I just given you the answers there. So it assumes that the extraction rate is constant, that it's going to always be at the same pace. So in a way, if it's a constant percentage, so that's one thing, but here I just said it's a constant value. So constant value, it means we have 47 years left, but if it's a constant percentage, then I have infinite years left in front of me, because every time my 2.15% of something smaller, it means that the oil consumption will be smaller. So should we expect that we're going to extract the same percentage per year, or the same absolute number per year? Probably the same percentage. Why? Because the price is going to go up. So I discussed about it a bit in the introduction. And so there's a very simple model for this. It's called the stock flow asset pricing, which says that price is some function, some positive function of how much do we use divided by how much do we have left. So it's a function of this percentage there. And of course, so the more we use, then the higher the price will be, and the less we have, the higher the price will be. So as the goes down, prices will go up. Consumption will then go down because we have less of it. And since the price is higher and the consumption is lower, then what does that mean? Either we just use less energy. I doubt it. Could be, but more probably is we're just going to move away from oil to other energy sources, or become more energy efficient. That's something that's quite likely to happen. So there's just a question for you. So question. So it's that bad for future generations, for instance. I mean, all resources, all non-renewable. Is this a problem like pollution is a problem, for instance? Somebody has an opinion about this? Because that's something that a lot of people worry about. They say, well, now we're just burning all the oil and there's nothing left for future generations. If the consumption goes down, yeah. Yes, it's true. But so my question really is it something that's inefficient from an economics point of view to leave the market as is. Yeah, okay, I'm going to write it again even more. If we let the market exploit, should the government, so yeah, I'm more precise here. This is just to say economists have many things on their plate. So we have all these sorts of resources to deal with, non-renewable, non-living, living. So are non-renewable resources being exploited? Should we care about this? Should we tax them, for instance, or not? No idea. Oh, somebody has said, so it could be a problem if we don't find an efficient renewable resource. Same amount of aggregate probability, yes. All right, so that's exactly the kind of question I had in mind. So my short answer, probably not. So probably that's something that we don't have to worry about. Why is that the case? If you think about it, imagine that we know for a fact that in 50 years, then oil is going to have some magical property that's going to cure cancer and create eternal happiness for everybody. So in 50 years, oil is going to be the most precious thing we can ever hope for. And if we burn it at this rate, then it's just the stupidest thing ever. So we should really worry about this. Question is, would the free market burn it if we knew that oil was just going to become so precious in the future? Well, if that was the case, then what I would do is go to the bank and borrow a lot of money and buy as much oil as possible and bury it in my background in some tank. And then I would just keep this as in inheritance for my children, because I know that in the future, there is no oil left except what I have buried in my backyard. So they're going to be super rich. So that's an awesome idea. But then is that what's going to happen? Well, the thing is, if that's the case, if we anticipate that oil is going to be crazy useful in the future, then I wouldn't be the only one to do that. Everybody would want to do that. And so in a sense, everybody would want to buy oil today. So the price of oil today would go up. So what my point is that all of the expected future use of oil is already factored in the price today. It's if we believe that stock markets have some rationality in them, in the sense that they incorporate new information that comes in, then the price of oil is the perfect price. It's the price that reflects its use today and its expected value tomorrow. So, so in a sense, it doesn't. So it's not something to feel bad about for future generations. It's just we exploit it, but then they are not going to have it in the future. Yes, exactly. And so it would be bad for if there was something unexpected, though. If we realize all of a sudden that we really should have kept a big amount of oil and we didn't, then it would be bad. So if no crisis, unanticipated, then today prices reflect the best use resource today and the best anticipated the resource today and in the future. So it's not really something that we should care too much about. What we should care about, though, is market failures, like greenhouse gases, for instance. How do you write greenhouse gases? I'm not sure. Let me Google that real quick. Okay, he writes it in one word. So I'm going to greenhouses like this. Yeah. So this is where economists should restart intervening. This is the real problem. This, not really. All right. So this is the circular flow of the economy. So I'm not going to ask you to remember this by heart and draw the drawing perfectly at the exam. So this is just to, some people have more of a visual way of learning. So you can think of this as the whole environment, and we get natural capital from that. It's used by producers to produce goods for consumers, goods and services for consumers, but it creates residuals which can be recycled, or if they can be recycled, then they are treated in waste treatments and discharged in the environment. Of course, sometimes it's just sometimes there's just an arrow there because we don't if we don't have money, we just release pollution, but normally we should treat it. And so consumers by themselves to produce waste that may be recycled and used again by producers, or discharged, and then there can be waste treatment again of the discharges. All right, so that's the link between the environment and the economy. So economy gets something from the environment and discharges something bad in the environment. So it's usually not a love story between the two. Usually they're so economy gets a lot of environment, but doesn't give back many positive things. All right. Yeah, so what we mostly care about in this class is residuals. So natural resources, yes, but mostly residuals. So pollution and CO2, of course. And how to reduce or mitigate their flow so they have less damage and they make less damage on the environment. And we need to find ways to change the way that economic activity is done in order to reduce the damages to the environment and protect natural capital. So no big complicated aspect to that. All right, so now we dig deeper into the type of pollutants that we can have. So this was just talking about resources up to now. Now pollutants. Again, I want to be as precise as possible so that we can talk about things in a pertinent manner. Because each pollutant is different, and the characteristics of each pollutant dictates how we should be dealing with them and how harmful they are. And usually people not necessarily have a good grasp on how bad or not so bad something is. And if so, and even so people who get elected, for instance, they will say, so there's Anglade. What's her first name again? Well,
Dominique.
Dominique Anglade of the Liberal Party. So she has a plan to promote some to have some environmental policy. So is it the most sound or not? Is it something that's catchy or that would make it or look hip? Or is it something that economists would say is really useful? So to judge this, we really need to just compute stuff. And later on, when you have to do your benefit cost analysis, then it's going to matter how much, if you're saying, oh, this is the intervention I want to judge, then the first step is to say, okay, so you want to reduce this sort of pollution, why? So you have to say why it creates a damage and why it's something that's really bad for the environment. It's a bit like if you want to go to court because you allege that that some person may wrong you in some way. Well, the judge is going to say, okay, so prove me that it was intentional, that it really hurt you in a bad way. And then you have to quantify this in some ways. Otherwise, you're not going to win your trial. So this is the same thing. So if you describe the sort of pollutants that you care about, then this is a good thing to be doing. So first way of classifying is accumulative pollutants versus non-accumulative. So here what we're saying is how long do pollutants stay in the environment? And of course, the longer they stay in the environment, then the more worrying it is. Plastic, we can more or less say it's 500 to 1,000 years, but very imprecise. Even there are museums that had some new some modern piece of arts made of plastics, and they thought, well, at least it's made of plastics, so it's not as difficult to keep as a painting, for instance. But sometimes the plastic made at the time, it was not of super high quality, and it's now starting to degrade. So it may be even shorter than this, but of course, maybe it's longer. When it's combined with other things, it may be longer. So that matters, of course. And the thing is, it's just plastic have been invented for a few decades, so it's really a short time span to have any idea really of who knows, maybe it's 1,000 years, but people everybody uses the same numbers that are just estimates, but no one really knows for sure. Radioactive waste, of course, that's extremely scary. But are all radioactive wastes the same? No. Some have half-lives of 30 years. So half-life, just to, what's a half-life? So it's the time after which half of a substance has transformed into something else. And we should almost use this for everything, because it's not like you have a bottle, you wait 500 years, and then all of a sudden it changes to dirt. You know, it's going to degrade slowly, and you could see, yeah, if I wait 500 years, then maybe half is disappeared, but half is still there. So everything is sort of measured in the half-life. So what does that mean? Well, it means that if you are thinking, oh, I have two choices of nuclear power plants. One creates a residue that have a half-life of 30 years, and the other has like plutonium-239 has a half-life of 24,000 years. This matters. It really does. And the thing is, for this, we have very, very good estimates. Because that's just the physics of particles. We know exactly how it is. And if you think about it, if you produce some some nuclear waste and you say, oh, it may contaminate water and we should care very much about how we store it. But, nuclear power has been going on for about 30 years in some instances. So for this sort of residual, already half of it would be disappear. So it still means that half of it is still there, but the time horizon isn't too bad. This is bad, but we should be concerned with it. Greenhouse gas is the same. So CO2 has a half-life of maybe 30 years in the atmosphere. So that's a very accumulative pollutant, and the CO2 that's emitted now is going to have its most if it accumulates with the rest, then the damage is going to accumulate over time for decades. So we should really care about this. Methane is it's about 6 times worse. But shorter life, half-life. So who knows what's best or what's best, what's worse. So I think we should both try to mitigate it, of course. But you see that after 9 years, it's already half has been reabsorbed or transferred into something else. So it doesn't stay as much as long in the atmosphere. All right. So non-accumulative pollutants are short-lived. They disperse and assimilate quickly in the environment. So noise, unpleasant odor, dust. So this, obviously, that's much, much less worrying than the other. Although noise, that's sort of been a growing thing that I think it's interesting because that's something that nobody cares about, or few people care about. But if in some countries they are starting to ask themselves, so does that really create stress for people living in a city, for instance, if there's a lot of noise there? Should we try to mitigate it? And they have some estimates that show that yes, people do feel much, much better if we're able to reduce the noise. And the big part of it is cars, of course. So we shouldn't neglect that. Yeah, busy airports is So it's we kind of say, no, I'm strong and I don't care, and as long as I can sleep, I get used to it. But still, it's there. So of course, accumulative pollutants are harder to address if we don't, as we must consider past, present, and future emissions. So now the climate change we are experiencing now isn't because of what we did this year. It's because of what people have been doing for the last 30 years. And what we're doing now is going to have repercussion in the future. So just to show you how the climate system is persistent. So this is obviously we don't have, so I'm not going to ask you crazy questions about this, but I just want to put your attention on this thing there. So this is the history of records of temperature and ice volumes for like going back super long. So here is 120 million years ago. This is 20 million years ago. So I think the dinosaurs, I don't know when they were. Anyways, who cares? So, but what's interesting is this PETM, that's the Paleolithic, Neolithic thermal maximum. No, Paleolithic, no. What I mean is Permian. Oh, I don't remember. Okay. In a few words, what I want to say is in this short period there, you see there was a spike in temperature that looks very strange. And people say, yeah, it looks like there was an emission of rapid emission of temperature. And the temperatures climbed by as much as 6 degrees Celsius. So it's, and they estimated that about 0.2 gigatons of CO2 had been emitted during this period per year in the atmosphere. But then the question is, how long did it take to go back down? So did it go back quickly or not? Well, this is a scale of millions of years. So just this blip, it looks like it's short-lived, but it's about 200,000 years. So if you think about it, it took about 20,000 years to emit, but 200,000 years to reabsorb. So what I'm saying there is, if we put CO2 in the atmosphere and we let things go on, it's from our perspective, it's just forever. Really, 200,000 years. There's just it's just get used to it. You're there's no perspective that it's ever going to go down. Yeah. So these are the numbers. So yeah, about 2.2 gigatons per year. And the thing is, so during that period, 0.2 gigatons of CO2 were injected per year. And today that's 10. So we emit 50 times faster. So still we would have to emit for a long time, but not all that long to get this crazy impact on the climate. So it's persistent. You have to deal with it. All right, local versus regional versus global. So of course, the more local it is, the easier it is to deal with it, because they only affect one small area. So you can think of a lake, for instance. If you have your neighbor, you're on a lake and you have one neighbor, and the neighbor just dumps residues in the water, then you just go to his door and say, yeah, please, could you be nice, and can we come up with some ways to deal with that? So that's easy. But if it's regional, if it's global, then it's all that much more complicated to deal with. Yeah, so also the pollution does not travel to other areas. So that way the people, the interested parties are not that many. So. So it's easy to have everybody around the table and discuss, have a chat, and usually you can resolve things. Then that's so noise again, land degradation, ground level ozone, smog. Since it stays underground and it doesn't travel too much, so it's something that's a problem in the city, for instance. So you can sort of deal with it in the city. Otherwise, it's. So regional and global pollutants are way more complicated. So because they can travel long distances, so it means that the person who pollutes is generally not necessarily the person who has to suffer the problem. So that's what makes these problems ever more difficult to deal with, because you always have at least one person who doesn't care, and then what do you do about it? So regional, you have acid rains, smog, but still. Yeah, we were able to deal. So a friend of mine was living in Mexico City at some point, and she said that in Mexico City, that was the only city at the time where you could see the air that you breathe. But now in Mexico City, they were able to implement quite stringent rules on cars, and the air quality is much better. But then what happened is, the same phenomenon happened, of course, in Beijing, for instance. In China, they had huge problems. So during the last Summer Olympics there, it was just so bad. So they had to make a lot of effort. But it's regional, so you can manage it. Global, it's just worse. Global greenhouse gases, GHG. It's greenhouse gases. But still, in some instances, we have been able to deal with it. So ozone depleting from CFCs. This we were mostly able to do it because well, we could talk to each other, but also there were alternatives to CFCs to use in fridges, for instance. Now your fridge can run even though you don't have CFCs in it. So the problem with greenhouse gases is that, as we're going to see, the alternatives are still expensive. All right. Yeah, so local problems are easier to deal with than regional or national problems. So Elina Rostrom, yeah. When did she win this? I don't remember the time, like a decade ago, maybe. First woman to win the Nobel Prize, and plus she's not really an economist in the sense that she's more of a, I don't know, political scientist maybe. So what she looked is how tribes in many countries were able to deal with local problems. And so problems of common shared resources, for instance, and how they were able to, without any sort of economic institution as we would have them in our countries, they were perfectly able to deal with their problems together. Yeah, so our point is we shouldn't send a Canadian economist to some African country and he would say, no, but you don't understand, you should do this or that. They already do pretty well for themselves and they have their own way of doing things. So yeah. All right. Something that's related to local or global. Oh, by the way, what time is it? Yeah, it's 30. All right, so we can stop here and we're going to finish this chapter next time. We're right on track. No worries. All right. Question, comment before we finish? So of course, no. Yeah, exactly. So once I finish a chapter, I'll post it online. And for now, there's no real exercises for you to do. It's because it's really descriptive. So the way you would do this is, I guess, you study it and you learn it as well as possible. So if I ask you some questions during the exam, but yeah, when we start with the technical stuff, then I'm going to give you exercises to do. All right, so have a nice day, everybody, and I see you soon. And oh yeah, and by the way, I've checked the Concordia website, and it looks like we're going to continue with online teaching until February 2nd. So yeah, That's COVID for you. All right, so thanks everybody, and have a nice afternoon.